Hi, linear algebra students. So this is a very important exercise about matrix multiplication, more specifically on its properties. And I'm asking you to prove that matrix multiplication is associative, which means A times BC is equal AB times C. Okay, so what I mean by this is that the order at which you multiply doesn't matter, because what this sides mean is multiply B by C and then A by the result. So this is what this side means. And the other side means pretty much the opposite. You multiply A and B first, multiply A by B, and then multiply the result by C. Okay? So overall, when you put these two things together, it really just means that the order doesn't matter. Okay? Okay? So, now will I erase this? Okay, I won't erase this yet. I will just give my main message. So I wrote a detailed hint on how to approach this problem. So my expectation is really that you try it with the hint that I gave to you. But if not, no worries. Just watch me going through the steps here, and as long as you understand how to do it in the very end, I'm happy. Um, the hint that I was giving you in your notes is basically to do it column by column. Okay, so let's actually write this down. The idea. Okay, we prove that the jth column of A times BC and the jth column of A, B, C. We want to prove that they are the same regardless of G. Okay, if we are able to prove that, it basically, the argument that we're going to write, being valid for every possible column of these two matrices, will mean that these two matrices are actually the same. So that's the way we want to build the proof. Okay, now I'm going to erase everything and jump in the proof. Okay, now the reason why we want to go column by column is because we know how to compute the matrix vector product very well. For example, if we consider the column Cj, and that's what we're going to do. So let Cj be the jth column of C, right? Okay. So what it means is that BCJ, by the definition of matrix multiplication, will be, so is the jth column of BC. Okay? And then we also know that A times B Cj, again by the definition of multiplication, will be the jth column of A times B times C. Okay, so is the jth column of A times B times C. Okay, for now, nothing mind-blowing. Actually, we did the easiest part, which is to multiply the matrices in the reverse order, because that's how matrix multiplication is really defined in some sense. We are really taking this as the input, then the output, then the output, if that makes sense. So this is really the easy part. The hard part is to prove that this corresponds also to the jth column of this. That's the hard part, okay? And now here we go. This right here, okay, so this is a matrix vector product, right? So this is a matrix vector product. And as a result, we can write that A multiplied by BCJ, so I will color code this entire thing in green so you'll know what I mean, is actually the same thing as A bracket. So it's the linear combinations of the column, it's the linear combination of the columns of B with weights being the C's, right? So in other words, and here I have to be very careful of my notation, okay? So I'll write B1 and then plus all the way up plus Bn, let's say. So here we're kind of assuming that B has n columns, which we certainly can. There's no problem with that. And then the weights, okay? So this is a little bit tricky. So J is the column. So we're going to write C1J, B1, and then CNJ, Bn, okay? Like this. All right? Now we're going to use the fact that the matrix vector product is distributive, okay? So yeah, we're actually gonna go slow, okay? So we're gonna use here matrix vector product is distributive, or actually, how can we say this? Is linear, or let's just say that we're using the properties of the matrix vector product. So from the properties of matrix vector product, so these we proved in the first chapter, right? We can write this as C1J AB1 plus all the way up plus CNJ ABN, okay? So in other words, we're distributing the A over all the terms, and since the C1J and CNJ are scalars, we can actually take them out like this, okay? Now, we're going to use again, so this right here, these are the columns of the matrix AB, right? Actually, let's write that. So these, right? These are the columns of AB, okay? And what this means is that what we have in reality is AB multiplied by Cj. And this right here is by the definition of the matrix vector product. So by definition of matrix vector product. Okay. So I'm almost done the proof, as you can see. I'll just erase this top part. So I'll erase up to here. And as you can see, so since A, B, C, J, okay, so this is obviously okay, actually, yeah. So, but A, B, C, J is the jth column of AB times C. Okay? And this again is by definition. So, by definition of matrix multiplication. Okay? So basically what we proved, so is that the jth columns of AB, A times BC, and of AB times C are the same. And this regardless of J, right? The fact that we used the CJ didn't enter in our argument. We could have used C1, C2, C3, all the way up, right? Are the same regardless of J. And unfortunately, I'm stuck erasing this to finish the proof. So as a result, we have A times BC is equal to AB times C. And this is what we wanted to prove. All right, I hope this helps. So just to summarize a little bit, the idea of the proof was to replace this matrix C by the vector Cj, just to take like its jth column, just because we already know very well the properties of the matrix vector product. And from there, we can deduce the associativity of matrix multiplication. I hope this helped. See you in the next video.